Hey everyone, and welcome to another episode on the Sencera podcast. Today, super excited to get into the company Sencera. Today we have Mike Draper with us to give us the rundown, get us an inside look at the company and really understand the really innovative things they're working on. So with that, Mike, thank you for being here. How are you doing today?
Good, Quade. Thanks for the invite and appreciate you giving us a chance to kind of broaden awareness on what we're doing with Stirling heat pump advancements and solving what we believe to be a pretty big problem. Um, so thank you.
Yeah, of course. Glad to have you on. So getting right into it, would you be able to introduce yourself, your career a little bit, and how you came in contact with Sencera?
Sure. So I am about a 25-year experienced business development professional in the Silicon Valley. Well, over the last 20 years, I've been focused on climate tech, in particular hardware. My take was that the hardware piece of the puzzle in terms of reducing global emissions, global warming, in terms of the areas where emissions and industrial process came together, where were the pieces that could be disruptive in reducing what would be global warming potential. And this was so we Sincera's had actually sort of almost two lives. I had so my background is technology, software, hardware, working directly with founding engineers who are innovating disruptive solutions to climate problems. And so, in particular, when I had met Rusty Jewett about 18 years ago, um, Rusty's background and frankly success, he had enough. When founders do a startup to exit, you want to sort of see the path of what they had promised and what they delivered, and what became of that hardware innovation. And I'd seen what Dr. Rusty Jewett had done, our CEO, in terms of some very successful, uh, I'll say, hardware development that had applications in for climate tech, which was at that point solar production. So as you mentioned, Quade, your experience with solar, um, we were producing one of the lowest capex solar panels for amorphous silicon back in 2008. Um, Actually, the lowest capex per kilowatt um, in the country. And the unfortunate part was, and at that point, and that was about an 18-month life cycle from the cell development to the solar panel module production. And so we had gotten an offer for an acquisition. We actually the Our lead investor advised that we not take the offer, and unfortunately, at that time, China had dumped or started dumping a lot of solar panels to the point where we know the effect it's had on sort of solar manufacturing, solar panel manufacturing. Uh,
Right.
so, uh, come to find, we looked at then what are the areas where we saw a lack of innovation and where we could develop more commercially viable hardware that could be, um, I'll just say, uh, make a big difference in reducing global emissions, but also applying what would be um, a a different type of cycle that could be, um, I'll say, readily commercially acceptable and be cost effective. So we saw refrigerants is if you looked at Project Drawdown as a reference, it's the number one cause of global warming. if we were to eliminate refrigerants, we would be reducing global warming by about a 25% margin. And looking at the behind the refrigerants, the cycles, the thermodynamic cycles, we basically, when I say we, Dr. Jewett, three engineers that have worked together for over 15 years, um, identified and went through the gist of the various cycles in from gas, um, McCann Erickson, Rankine, um, Joule Thompson, um, and finally came about the realization that the cycle that was the most optimal and the cycle that would be, I'll just say from the thermodynamics, if you remember, if anybody went to thermodynamics engineering class 101, you learn about the Carnot cycle, which is the theoretical optimal, right, for let's say the transfer of heat and cooling. And that is from the standpoint of like the bar, the benchmark. That's where every um, HVAC OEM or every system solutions provider, they want to get to the most efficient, piece of the performance. And what we saw was a market that where it was dominant by ranking refrigerant heat pumps and looking at refrigerants, understanding that the hydrocarbons behind these refrigerants um, were, they last 100 years. They're environmentally, they have health impacts that are unsafe. And we had, in my own experience, I'd been dealing with plumbers and HVAC contractors, trade families that were dealing refrigerants on a daily basis and basically had, um, I'll just say, if they kept telling me if there was a better way, a better system, and we didn't have the exposure of refrigerants, Mike, that would be solving a big problem. And so I heard it from the market. Rusty heard it actually. Dr. Jewett had actually heard it from one of the Dutch housing authorities that had suggested that if you could come up with a heat pump that was refrigerant free and more efficient, with a cycle that was, I'll just say, higher performance and cost effective, you would that would be very key for us. And so we looked at we basically identified Sterling as to be the um, that it's a 200-year-old cycle. We didn't invent it, and a lot of people don't realize that Sterling is in today's market. They're commercially used by companies like Cargill, GE Medical, AstraZeneca, for the application purposes of reaching very high delta T applications, for areas like pasteurization, sterilization, drying, cleaning, where we're talking about temperatures from 72 C to 150 C on the hot side, and then on the cooling side, where Sterling's have really sort of prospered in cryo cooling, on cooling like semiconductor chips and areas like that. So Sterling has been around, and at a 200-year-old cycle, it is known to be the most efficient. The issue and the biggest challenge has always been the cost, because it is because the older Sterling architecture from the lineage of, let's say, Philips, is the main architecture that's still used by the Sterling peers in today's market. So these systems are massive, very heavy, and have low power to weight ratios. So our challenge was, okay, how do we take Sterling and reconfigure it to be more commercially viable, and then also be able to be scalable for smaller applications to larger industrial applications. Everything from going into a heat pump for an EV car to a to a large industrial steam application for a food and beverage company that needs to be at 200 C at a high temperature. And so, but wants to have it cost effective and performant and reach a COP performance that can, I'll just say, minimize the operating cost in that process. So Sterling, just as a primer on Sterling, have you heard of Sterling before?
The engine, I know it's had many uses over the years, but I don't know too much about it, so I'm excited to dive in
Okay,
and understand.
great. So the Stirling cycle itself is a heat pump. It basically works by compressing and expanding a working gas in a closed system. So we're utilizing heat sources and sinks to achieve a temperature differential. And ideally, it's high delta T applications where these Stirling systems really shine. We don't use refrigerants. So unlike a conventional heat pump, our Stirling heat pumps don't rely on phase changes, meaning boiling and condensation of a refrigerant, making them basically more environmentally friendly. We rely on nitrogen or helium. Our pick is nitrogen because it's cheap, it's available, it's non-toxic, and it's non-flammable. So it's this is environmentally safe, and at the same time, as far as what we could do to in the there's a lot of intellectual property in terms a lot of IP behind the Sencera Sterling in the areas of designing heat exchangers, regenerators, um, and basically a rotary design to replace what was the older architecture relying on linear motors, springs, coils, a lot of moving parts that created more complexity to the process and cost because their weight was, I would say again, these were factors and variables that made them not commercially viable. So Dr. Jewett was actually brought in to the Sterling, his background has been for the last 20 years um, from his fellowship days at Sandia Labs, where he looked in New Mexico at these Sterling dishes that were actually not working. And for any engineer that looks at at a system that doesn't work but has curiosity, Rusty had gone into then understanding, how Sterling works and tinkering with it enough to the point where, um, his background in thermodynamics comes from the semiconductor side. And if you're looking, so what's the difference between a Stirling versus a Rankine refrigerant heat pump? Well, Stirling, it's a closed gassed single phase cycle, and it requires the disciplines of physics, chemistry, mechanical, and electrical. Almost all four skill sets at a very high level. And so, where a partner, SunPower, was a NASA Sterling partner, in which Dr. Jewett then designed, with our existing founding team, helped design the TRL-9 commercially used Sterling engines by NASA. So up today in the space shuttle, if we look at the pictures, those space shuttles have our Sterling engines that have been running for over 500,000 run hours, with over 20,000 engines, extremely reliable and extremely efficient. These are very high performance. They're used in remote power systems, infrared sensors. Um, and so again, the issue has always been cost. These engines for would cost for like say a 100 kilowatt or unit, or even you're looking at a very high six-figure cost, $100,000 cost. Not the type of cost for, let's say, a 10 kilowatt Stirling unit that NASA would pay $100,000 for, right? A heat pump in your home for 100 grand is really not going to get us far. So, big challenge. How do you reconfigure it and be competitive to the market? And so, what Dr. Jewett led the build out of the first of the Stirling engines at NASA, and realized that the limitations in the architecture were not going to enable what he had seen to be an opportunity for adaption on a more mass commercial scale. Um, And so we took it upon ourselves over the last, it's been almost 15 years really, of engineering, hardware revisioning, to the point where probably 3 or 4 generations now of hardware configuration to get to a point where we have a Stirling heat pump that we can manufacture at the same cost as a Rankine refrigerant heat pump, deliver a COP efficiency that can reduce the kilowatt usage and the cost to the consumer or the business owner, and deliver a zero carbon footprint, and also have less noise. These are extremely quiet. These machines whisper. So they have the benefits of higher efficiency, with our configuration on a rotary design, lower cost, and basically have um, the benefits of uh, removing refrigerants that make up about 55 gigatons of the global warming problem that we're facing today. Um, so that's kind of high level of how. So we have basically self-funded and have sweat equitized this company to date, um, in building out the first prototype, that we brought into, basically this is the picture we see here is a 10 kilowatt unit. This would go into a home. It's about, I think it's about 3.5 feet, about, I think it's about 16 inches in diameter. Those measurements I'll have to configure, but these machines, at a 10 kilowatt unit, they're about 50 pounds, maybe 47 to 50 pounds. So they're extremely light, and we've taken the weight because again, we're using just off the shelf really hardware that is cheap and is reliable, and that the real secret here is that with the redesign of regenerators, heat exchangers, the rotary engine or the rotary motor, um, we now have a heat pump that can deliver 4 to 8 times more heat or cooling than a Rankine refrigerant heat pump in today's market, and do it at the same manufacturing cost. So our goal is to bring to the market a cost-effective refrigerant-free solution that can also drive the um, the areas to meet extreme temperature variations. The demand in today's market, is for higher temperatures, is for these heat pumps to be able to work when it's cold or work when it's extremely hot. we're seeing our summers get hotter. We're seeing our winters get colder. Um, as we looked at the Rankine refrigerant heat pump, we realized its limitations in being incapable to deliver performance when we really need it, when it's minus 30 in Minnesota, and any Rankine system is typically going to be um, the COP efficiency is going to be close to zero at an extreme temperature. So having a heat pump that could adapt to these temperature ranges and be cost effective and remove the refrigerant problem, um, we saw to be valuable. And for the rate for the customer, it's we're reducing an OpEx of utility cost that for today, we're faced a market where there's a new administration. um, Heat pump rebates are being rescinded. The Energy Star program, as of 24 hours ago, has been wiped out. Um, and the folks that are making the refrigerants have also been subject to uh, the products like 454A refrigerant that's used by the industrial and commercial folks. I believe the company that makes that had just increased the price by 45%. So for a contractor that's dealing with, the variable costs of a refrigerant that is number one toxic, number two is going to be a variable cost that is likely to increase, and number three is facing a customer that is going to be having a hotter summer or a colder winter and needs a heat pump that's reliable and works without $500 bill at the end of the month. And it's interesting. So I'm here in San Francisco where the temperature is extremely ambient. It's usually, as you know, Quade, it's a 50, 60 degrees, 70 degrees. Do you know the few times that we use our heat because PG&E has escalated our electricity rates by 4 times over the last 3 years? Our bills are still $400 for a 200 square foot house. And that's true with every house on this block. So not just California, there's a lot of states where the folks are being subject to a very high rate. They're in a very cold climate or a warm climate, and we can reduce that cost with a higher efficiency. And that's just from a consumer standpoint. Our journey in the market has been um, that we've gone to both end user and the OEMs, and what we've come back to is their need to, number one, they're facing regulatory changes and dynamics with some of these refrigerants being banned. 410A coming up, and others that have been banned over the years, where they need to make a change, and at the same time they have a need for higher temperature applications, where again, ranking, if you're looking for boiling or even just pasteurization at 72C, um, a multiple phase ranking system is going to cost, it's going to be a, I'll say, from a capex perspective, it may look attractive. From an opex perspective, if you compare it to what we're delivering in efficiency, there's going to be a greatly reduced cost. So um, our first global pilot partners are with OEM leaders. We're under restrictive NDA, so I can't provide the names, but they're brands that you know of. Um, we're building out pilots now to meet their needs for both a cold chain application and then for another would be a water heating application. And so with the cold chain application, this is to meet at like a minus 100 C um, cold chain temperature to for a particular market application to cool in the semiconductor market. Um, for the water heating, they're looking at again getting something that's more efficient to replace what a lot of the OEMs are facing, which will be the banning of gas furnaces for water heating starting in 2027 by the DOE. So the regulatory dynamics, the market dynamics, um, the question has always been, you know, when we're asked, like, Mike, why does Rankine refrigerant heat pumps dominate the market? Look, it's a 100-year-old cycle. It has been built extremely cost effectively, um, and at the same time, it's reliable. So, and that is these are these are worthwhile attributes, and Rankine will never be completely replaced. It'll always be in the market. But we believe that there is in what we've advanced with Sterling a viable alternative for a heat pump at the same cost to deliver more heat and cooling at a lower operating cost and do it more climate friendly. And so that's been our mission is really beginning to give the awareness that number one, a lot of folks are looking for solutions in heat pumps that are going to be more climate friendly. So they're going to supposedly sustainable refrigerants. Unfortunately, there's no such there's no such thing as a green refrigerant. The science is pretty clear. Um, and I don't think from the perspective of the HVAC, um, the HVAC marketplace, you know, what do customers want? They want it cheap, they want it reliable and working when they need it, and they don't really want to think about it, right? They want these things to be running when they need it. And it's I think the beginning, if you were to ask most of your audience, what's a heat pump? What does it do? How much do you know about your existing heat pump in your house? I don't think we pay a lot of attention to it. And so I think, getting audiences more attuned and aware of heat and cooling innovations that can be, I'll say, more climate friendly, more pocketbook friendly, and really have probably more contribution to reducing global warming in a market that likely is where the variables of temperature, our summers are likely to get hotter. Our winters and the extreme weather patterns that are following are likely to continue. And if you we are to continue on that assumption, a Stirling heat pump solution, we believe um, can be a very fair service, a piece of hardware solution to help a homeowner or a business or industrial owner with meeting a heat and cooling transfer need that um, can be more, a more climate friendly, but to their interest really is not that much on the green side from our experience, even from the OEMs. They really don't care too much about the green side. I mean, some of them do, but most don't. They want it cheap, they want a low cost, and they want to know it works and reliable. And so our challenge again is going to be in our first commercial build outs with our two OEM partners now, is to go through now the validation process of what we've already proven in the lab. So the little 10 kilowatt unit you see there, that has been lab validated, third party lab validated by the University of Twente. That, we also see in the marketplace, many of the OEMs will, I'll just say, you have things like COP rating basis that they sell units on, or SEER ratings. Um, you know, I think there's something to be said for looking at what they're stating and then what they're performing in reality. Because when a company sells at a COP of 5, but when it's minus 5 degrees out and it's a COP of zero point 0.5, there's a fairly large differential. And unfortunately, ranking refrigerant cycle is limited. I mean, as far as that going back to the Carnot cycle, the theoretical optimal, Rankine maxes out at about 25%. The unit that you see in that picture there is meeting a 43% Carnot limit today in a prototype. And our target we tweaked a little bit on our redesign of some componentry that we believe we can meet a 60% efficiency benchmark of Carnot. And that would reduce utility bills. That would increase it another magnitude in terms of performance over what we're doing now. So from the market side, huge demand for high delta T applications where they need heat or cooling done at a very high temperature, and have it be reliable. And with Rankine, again, you've got multiple phases for the higher temperatures. That multiple phase refrigerants, the inefficiencies when you're talking about COPs at 150 degrees C or 200 C, they unfortunately they're not performers. They fail to perform, and this is where Sencera Sterling and Sterling in general has been. They're a proven performer. I mean, they're already. Cargill uses now to clean their steam clean. They're using it in a particular aqua farm in Norway, where they love it because the Stirling systems are helping them clean the steam boilers through very high temperatures. But you know there's a point where you need high temperature, but you're not willing to pay the cost. And for these companies, they needed the temperature, and cost wasn't a factor. If you need to cool a semiconductor chip, you don't care what it costs. You just have to do it, right? It's so that's where we've I think provided an alternative that is we believe can be market adaptive, and at the same time, there needs to be an awareness in the market that, and indeed, there's an alternative. The unfortunate, I think we also have experienced a certain amount of territorialness, I'll just say, around the ranking side, and we respect that. I mean, we're dealing with 30 year plus ranking mechanical engineers that are extremely, they're masters, the absolute masters, and they command our respect. The difference being we're taking heat and cooling to another level, with uh, with a more advanced and more efficient method of transferring that heat, with a cycle that requires higher disciplines beyond mechanical engineering. You have to know physics. You have to know chemistry. You've got to know your mechanical as well, along with your electrical, to be able to compact this package and develop this.
Well, thank you for that amazing high level overview of the product. It's super interesting how you guys took an existing technology. I mean, it was developed even more NASA. You developed it even more into, I mean, really something revolutionary. And it makes sense that there is, some pushback in those rankings and things like that. Well, thank you so much, Mike, for spreading this information and awareness of this product. And I mean, these problems are growing, like you said. As things go forward for your company and you start, testing with other companies or you start selling to other companies, what would be an easy and best way for a company to get a hold of you guys?
Yeah, best way would be, an email at info@sencera.com or my email, which I can put in the chat, or at mike.draper@sencera.com. Certainly, we welcome anyone in trade or customers that are looking for high performance heat or cooling solutions for either a commercial, industrial, home application. I would say we're probably, 16 to 18 months before the commercial entry. So there's some time, but I will say this: we have the OEMs that have aligned with us as pilot system partners, have validated and vetted what we've done to the point where they're willing to take development risk, and that has been a refreshing start in our entry. And likely the dealers under those OEMs will be privy to the access of our Sterling heat pumps through their dealer bases and eventually to their customers.
Thank you for that. I'll be sure to include that in the description for anyone wanting to reach out, look into it, along with the company website. But thank you everyone for tuning in. Thank you, Mike, for taking the time to share with us this product. And I hope everyone has a great rest of the day and they tune in on the next episode.
Great. Quade, thanks for having us. And anybody that would like to go to just Sencera.com to learn more, we welcome any inquiries and appreciate the opportunity to share our awareness.
Perfect. Thanks, Mike. Thanks, everyone. We'll catch you next time.